Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate playlist. Potential temperature. One of the fundamental thermodynamic properties in atmospheric sciences, yet never communicated to the public. You don't wake up and check what is the precipitation, temperature and pressure like today, and also let me see potential temperature. No, you don't do it. But potential temperature is extremely important thermodynamic quantity in calculations that we carry out in atmospheric sciences to get weather forecast, and then we convert temperatures back to regular temperatures so that the general public can understand everything properly. Why do we use potential temperature? Well, for the following reason. You remember from my previous video, we had Earth's surface, and here is the height, z, and let's say we have a parcel of air over here. And we studied how this parcel of air, if moved down towards the Earth, how it will compress and increase its temperature. So you see, if I start with this parcel of air over here, and it has temperature T1 and pressure P1 at height z equal z1, then when it comes to Earth's surface, it will contract, it will become smaller, and it will have some different temperature T0 and pressure P0. So as it is moving up and down under the assumption of adiabatic process, there is no release or acquisition of heat, both temperature and pressure will change. Question, fundamental question. Because the process is adiabatic, there is no addition or release of heat. Is there a quantity that is conserved? Is there a quantity that stays constant during these motions? Because clearly temperature and pressure are not constant. The answer is yes, and that quantity is called potential temperature, and we use Greek theta to denote it. This quantity is equal temperature, regular temperature, P0 over P to power R over Cp, where P0 is a reference pressure, soon to be explained. P is pressure in this parcel of air. R is, you remember, because this is for dry adiabatic processes, air is dry, so this is dry air gas constant, 287 joules per kilogram per Kelvin, and Cp is specific heat at constant pressure, 1004 joules per kilogram per Kelvin. So if we look into this equation for potential temperature, what is it? Potential temperature is temperature that parcel of air would have if dry adiabatically brought to reference level or reference pressure P0. In another way, potential temperature is temperature that parcel of air would have if dry adiabatically compressed or expanded to reference pressure P0. Now I tell you what is the reference pressure and you know everything. Reference pressure by convention is usually 1000 hectopascals or 1000 millibars. If you are using this equation, you should use pascals for pressure, and for temperatures you should use kelvins, not Celsius or Fahrenheit. And during dry adiabatic processes, theta is conserved. Theta equals constant during dry adiabatic process. What is adiabatic process, dry adiabatic process, explained in great details in my previous videos. So that means, because this holds, theta is very, very good tracer of air parcels. Because you see, I take this air parcel and I start moving it left and right, up and down. Temperature and pressure will change. So how can I inject some dye, some color into it so I can see it? Well, we don't inject color or dye, into this parcel of air to trace it. We calculate potential temperature, and if the process is adiabatic, more precisely dry adiabatic, then this quantity will be conserved, will be constant, and that's my tracer for the air parcel. So that's one way why this is so useful. It is a tracer, very good tracer. But that's not the only reason why that is useful. Look at this beauty. Let's say that this P0 at the surface is indeed 1000 hectopascals. So that is my reference pressure. And now let's do calculation and calculate potential temperature, let's say for this parcel of air over here. I think I have enough space here. Let us say that T1 is 13 degrees Celsius. This is T1, and you will see how we use also potential temperature. And let us say that this parcel of air is at this height, Z1, where pressure is 900 hectopascals. For your reference, 900 hectopascals is usually about 1 kilometer above Earth's surface. I told you temperature T1, we insert that here, we transform this to kelvins, 286 kelvins. You have R, you have Cp, you have P naught, you have P. If you insert everything here, you will get that theta is equal, if I go back to degrees Celsius, 21 degrees Celsius, if you do this calculation. I did it, so I remember. So this temperature T0 here, which is basically theta, is equal 21 degrees Celsius. You say, excellent, so what? So what? Now look at this beauty. I now tell you that ambient temperature of the air is TA. This is not temperature of this parcel of air, but temperature of the ambient atmosphere around this parcel of air. Now we have few options. Let us assume that this theta is, I don't know, let's say first, let me think, larger. Theta is larger than TA. If theta is larger than TA, then this parcel of air that came from 1 kilometer to surface will be warmer than the ambient atmosphere. Warmer air rises. So this parcel of air, if this is the condition that is met, will tend to go back from where it came from. That's why this is called potential temperature. Because we are saying potentially, if this parcel of air was dry adiabatically brought to the surface, what would happen? What would happen? Well, I'm telling you now, if it was brought to the surface and temperature of the ambient atmosphere was lower than the potential temperature, it would go back to where it came from. How about if theta is below TA? If I take parcel of air, I compress it I bring it to the Earth's surface, it compresses, it increases temperature, but still temperature of this parcel of air is lower than the then the ambient temperature of the atmosphere, namely this is satisfied. Well, in that case, parcel of air is colder than the ambient atmosphere and it would tend to sink deeper. In this case, it cannot sink deeper because I assume that here is the Earth's surface. But if 1000 hectopascals is not at the Earth's surface but above it, then the parcel of air under this condition will continue sinking. Theoretically, indefinitely, in the atmosphere it cannot be indefinitely because eventually it will hit the Earth's surface. And, of course, the last option, if theta ended up being exactly Ta, then nothing will happen. It will meet the temperature of the ambient atmosphere and it is at the same thermal conditions, so it will not tend to go back to where it came from, and it will not tend to sink. So we can, using the concept of potential temperature, we can study what would happen. And I told you when we have parcel theory, parcel of air theory, we always study what would happen. And potential temperature as a conserved quantity during these motions helps us to do that. If we had parcel of air if this parcel of air was at this height in the meantime, as it was traveling down and it came to this height, intermediate height, what is potential temperature? The same. It's conserved. You might say, how can you convince me it's conserved? I will convince you, let me erase this. I will convince you in the following way. First principle of thermodynamics says dq is equal Cp delta T minus alpha delta P. Entire video on that. Adiabatic process delta Q equals 0. Adiabatic process means, okay, I can use potential temperature. This equation over here is basically in differential calculus manipulated, integrated to get this over here. So the definition of the potential temperature follows directly from the first principle of thermodynamics. You might say, can you show that to me? Answer is no, because this is fundamental playlist, and you know if you're watching these videos, I'm not deriving equations. I'm stating equations. In my advanced playlist, I derive all these equations and I will soon do it. But you still might ask, okay, can you explain at least conceptually why during dry adiabatic compression or expansion this would be conserved? Yes, I can. Because look at this beauty. If this is 0, Cp delta T is equal alpha delta P, where alpha is 1 over rho, you remember. Look, as we are lowering this parcel of air, pressure is increasing. That means temperature is increasing. Well, potential temperature is temperature that accounts for this relationship. As you can see, it accounts for the change of pressure in this parcel of air. Yes, parcel of air will change pressure. This temperature, regular temperature, doesn't account for it in a way to stay conserved. Temperature is changing. But potential temperature normalizes this change of pressure against the reference pressure, and therefore it stays conserved under this assumption. And under this assumption means process is adiabatic. How about if the process is not adiabatic? How about if delta Q is not equal to 0? Well, then potential temperature is not conserved and you have to use some other concepts. But I discussed in my previous lecture that in many processes in the atmosphere this is quite good, very good approximation. So this is very important use of potential temperature, and this analysis that I outlined here is called stability analysis, atmospheric static stability analysis, and I will have separate videos describing statically stable atmosphere, statically unstable atmosphere, and statically neutral atmosphere. This is just small flavor to show you how potential temperature is used to assess these conditions. Lastly, I would like to go back to this concept of potential temperature being a good tracer for air parcels. Let's assume this is the surface of the Earth. This is height Z. And now we calculate potential temperatures for different heights. And let's say potential temperature lines look like this. Let's say this is theta plus delta theta, higher value. And now I take this parcel of air. And this parcel of air is moving in this direction. Look at beautiful application of potential temperature. Just looking at these lines, I can predict how it will move. You might say, okay, tell me how it will move. I will tell you. It will move like this. In other way, it will move to follow these lines. You might say, why? How do you know? I'll tell you why. Because theta is conserved, it's constant. Okay? For adiabatic processes. So if this parcel of air satisfies the condition of adiabatic process, then as it is moving up, down, left, right, doesn't matter where, this is satisfied. Well, to have it constant, it has to follow lines of constant potential temperature. Here is theta plus delta theta. This air parcel is in between, so it will follow a line of constant potential temperature that sits between these two. Does that make sense? I hope it does, because it's absolutely beautiful application. How it is distinguished from temperature? Well, as it is going here up and it is going down and again up, regular temperature will change, pressure will change, density will change, but potential temperature will not change. And because it will not change, it is forced to follow these lines. If the process is diabatic, then this does not work. Then the air parcel can deviate from these lines. But even that is beauty, because the amount of deviation helps us to determine to which extent the process is not adiabatic, but it is rather diabatic. These are just two applications of potential temperature that we extensively use in dry adiabatic processes. In some of the next videos, we will explain how we can extend this if the process is not just dry adiabatic, but if there are phase changes of water, namely moist adiabatic. Then potential temperature can be replaced by the so-called equivalent potential temperature, more complicated quantity, but don't worry, we will discuss it in details in one of the next videos. Please make sure to like and subscribe, share this video. This is very important concept for undergraduate and graduate students in atmospheric sciences and anybody interested in fluids thermodynamics. And until next video, goodbye.